Okay, let's get started. But let's get started sort of a flip-flop. We have to talk about our next test, right? Because our next test has to be the week we get back from break. It can't be the following week, right? Because the university policy is you can't have exams on the last week of schedule classes, regularly scheduled exams. So the reason why I'm saying this now is because it's a big decision. Do you want to have an exam Monday from 1 to 4 directly after break?
What the alternative?
So the alternative would be either the Tuesday during class or Thursday during class. That's the only one that I can get, you know. It's either Tuesday or Thursday, the week after break. So what is that, the week of December 1st?
So would that be a shorter exam?
It would be a slightly shorter exam, yes, because obviously we have an hour and 15 minutes. But it would be covering the same content.
But is it more compact or is it? Because if we have, let's say 6 questions during the lab, 6 questions. Now, if you have to make those 6 questions to fit in 1 hour, 30 minutes, is it less questions or the same 6 for the compact?
It would be 6 questions, but like less parts of it or less calculation. So instead of asking you to calculate, the zero sequence network fault current, I might say draw the zero sequence network, and then you wouldn't have to calculate the fault current, something like that. So it would be the same content and delving into the same areas, but not as much possibly calculation or not as much where you have to dig into things. But I can only give you about an hour and 20 to 25 minutes. I can't do a full hour and 30 because people have classes before and people have classes after. And remember, everything has to be equitable. So if you can say, hey, I can get here at noon and I can stay till 3, great. But does everybody else in the class have that feasible option for them? Most likely they do not. And I've tried for years in the past, which is try to set times up at night. We have 40-something students in this class. So the likelihood of everybody having a 3-hour window available on an evening is 0. So I don't even try anymore, is basically what I'm saying. Not that I wouldn't be happy to do it. You can't do it. I've tried too many times and it's never worked.
Do you think we do worse on the shorter exam? Do you think we need that extra time?
I don't know, because for me, when I would take tests, I would feel pretty comfortable doing the material. So the amount of time and just doing concepts with me I would actually do better. But if you're not understanding the material as in depth or as thoroughly, you might feel panicked that I've only got an hour and 20 minutes to do the test. So I panic, and as a result, I don't do as well. So that, again, I'm not trying to avoid answering your question. I just don't think it's as easy because everybody gets test anxiety, right? And if you have a 3-hour or 2-hour and 50-minute window, your test anxiety experience is probably going to be different than if you had an hour and 20.
If you don't know, you don't know.
Well, sometimes you can work it out. I mean, it just depends. Like sometimes you sit down, you think about it, and it dawns on you. Maybe, I don't know. But that's why I'm making this offer, because you're getting back from a long break, right? And, a 5-day break from school. How much studying are you going to do over break?
I like the idea first, but they do.
Okay, so before we do that, because TV Land should be able to vote, unless you want to just completely ignore them, right? Because they don't talk much. I'm kidding.
Yeah.
Let's do a poll. But some people live in like different parts of the country, so that's not that easy.
Yeah. Yeah.
I have a question, actually.
Yes.
So if it was on Monday versus Tuesday and Thursday, would you have the same option for like bonus points in the exam? Because
Yes.
If it's on Tuesday, are we going to spend Monday lab period reviewing?
Well, that would be the next question, is when would you want to do a review? So the first thing is, let's figure out when the test should be, and then we can talk about a review. So again, you asked really good questions that I'm not trying to avoid answer. I just don't think it's that cut and dry. So, all right. So
Yeah, Tuesday.
Oh, I gotta change it. I gotta edit it. How do I edit it here? I don't know how to edit it.
If you do, okay, or week long.
Let's take the same thing, so delete it.
I'll edit it this way. And then I will delete the old one.
Apparently that's not an option.
Yeah, figure that one out. Okay, well,
You can delete the copy.
They call it.
I can launch it.
You can.
All right, time to vote. For those of you in TV land, here's your chance to vote. Now, here in live and in person, you have the same options. Who votes for Monday during lab? Who votes for Tuesday during class? Who votes for Thursday during class? Okay, so Monday wins. Because 7 plus 5 is 12, right? So we're gonna do it Monday during lab. Everybody understand that? Which means most likely, and the only time we can do the exam review is next Tuesday. And I won't be here that class, so I'll record a video, or maybe I'll try to do it live. I'm not sure yet, but I'll do an exam review. And unfortunately, that's the only time we can do it because I need this class and next class to finish covering the material that's going to be on the exam. So unfortunately, it's going to have to be Tuesday, which I know is not great timing for everybody because it's right before Thanksgiving. But that's part of the thing about having the exam right after on Monday.
We could all coordinate on that Sunday if we wanted to get out of class.
To do what?
Like we in the class could just coordinate for the day before, or maybe that Monday morning we get together.
Oh, yeah, what you do for studying outside, that's totally up to you. I thought you wanted to do a Sunday session, which I could support, but again, it's, most people won't be able to make it. How many people are on their Thanksgiving and are gonna rush back to watch a class or do a class? It's nil, right? So I'll do the video and then you can rewatch it or go from there and get your questions answered that way. Yes, sir.
You have a lab that opens up today or tomorrow, and it's due next Wednesday, I think. How are you gonna do that?
I don't know. I gotta check and see what's going on. That might be wrong. I have the
Okay.
lab for the optional one. I have that opening up and that's opened up now.
Yep.
It should be available. I'll take a look at the other lab. So
Yeah, I don't know, do one.
the one at the optional lab, that's same time. Everybody said they wanted it Friday at midnight, so that's the normal time. Okay, anything else? Let me share the results. No, like I said, I won't be here, so. Everybody see the results? So Monday it is. Whoop, there's a comment. Okay. Yeah, you get to be your opinion, you can see, and this is all real time. And like I said, there were 5 in class for Monday and 4 for Tuesday. So 12 overrules the 8, those were close. And, we live in a democratic sort of society. So we go with what the majority of the people want, and that's Thursday. Or Monday, sorry. Okay. Thank you. So let's finish up our asymmetrical fault analysis. And let's take a look at what we're going to do with these 2 chapters. First thing we're going to do is we're going to take those sequence networks that we talked about. So those are individual networks where we looked at a generator and we had to look and see if the generator was grounded or not. And that's for any AC machine, whether it's a motor or a generator. If you want to figure out fault current contributions, or the zero sequence network, you got to look at the ground there, if it's grounded or not. Transformers were also the big one too, right? Because those could filter out zero sequence networks or filter out zero sequence current. So you really, really, really need to study the transformer diagrams that we put up to figure out, can I pass zero sequence current flow through here or not? Because when I'm trying to calculate equivalent impedances for each of those networks, I need to know, can current pass through there? Then we're going to look at the three different fault types that are asymmetrical: single line, double line, and double line to ground faults. Then we'll actually start to build sequence networks. So this is the next step, which is we have the individual diagrams, and then we're going to go ahead and take those individual diagrams for different components and connect them in a way based on how the actual network is configured, the electrical network is configured. And then we'll do the same thing we did the superposition approach, right? We'll solve for Y-bus for each of the sequence diagrams. We'll find Thevenin equivalent impedances. Is that what we need to do? And then we can do things generically. So we already mentioned in a balanced power system, you have positive, negative, and zero sequence diagrams, but there's no current flow and no voltages in your negative or your zero sequence networks. So as a result, or because the positive sequence network is the only one with a power supply, you have no connection between positive to negative or negative to zero. So if you had your diagrams, here's our positive, here's our negative, and here's our zero, there's no connection between those two. So over here in your positive sequence, you would connect that over with loads and all kinds of different things, right? Because you have current flow in there. But the zero and the negative sequence have no current flow. They're not coupled in. They're not interconnected. So what we need to do is, once we have an unbalanced conditions, now we can have current flow through those diagrams or those networks. And now we have to figure out how to connect the positive to the negative to the zero. That's what we're going to be doing today. So let's start by doing a basic diagram. Okay. We'll build the network and then we'll figure out, now once we have this network that experiences different fault types, where will the current be able to flow under the different conditions? So here's a simple system. You've got a generator that has a 400 amp resistor. Anybody ever heard of a 400 amp resistor? A lot of amps, yeah, for a resistor. But why would you have a 400 amp resistor in there? Don't you specify resistors in ohms? Usually, yeah. But just like in capacitor banks, I have a 1 megabar capacitor bank. I don't specify it in farads, do I? So what you're doing in the real world on utility systems is you're specifying these components in terms of what their capability has to be. Over here, if you have a solid ground fault, that resistor is going to limit the current out of that generator to 400 amps. So if I'm going to draw the diagram, I have my generator here. This is 20 kV. Then I have a fault to ground here. And so this is the earth. And then coming up through here is a resistor who limits the current to 400 amps. So R is equal to V divided by I, which the first thing you want to do is you want to say 20 kV divided by 400 amps. But didn't I say it's a Y-connected generator? Is 20 kV the line voltage or the phase voltage? Line. Always the line voltage. So if you want to know what a single line to ground fault current will be, what the max current will be, you had better divide that by the square root of 3. So if I take 20 kV, what I'm saying and what I'm writing down are not jiving. Sorry about that. I take 20 kV, I divide that by the square root of 3 times 400, and that's the actual resistor size in ohm. Okay, so literally when you're specifying the resistor, you don't specify it as an actual ohmic value. You tell the vendor who's going to make the resistor, hey, I needed you to limit it at 400 amps on a 20 kV generator. They'll specify the resistor for you. They'll also do a lot of the stuff for you to make sure it works. And these resistors are actually pretty fancy. It's probably the size of the desk, because 400 amps through a resistor, I squared R, generates a lot of power. And it's also made out of stainless steel, because as a resistor gets hot, if it's just made out of metal, it'll start to rust and corrode. So these are stainless steel resistors. They're pretty fancy ones. They're quite expensive. I've got pictures of them. If I have time, I'll put them up, but they're literally like, depending on how big the resistor and what power it needs to dissipate, you can go ahead and you can spec those out. So that's the first thing we need to do. Anything else that's weird on this diagram that we haven't ever seen? I hope not. Everything here looks like it's all generator ratings, transformer ratings. It doesn't look like there's a line impedance specified, but there may be one. We can figure that out. And then we have two loads. One's 200 MVA, grounded Y. The other one is 200 MVA, not grounded Y. And so you can see all the X values as well as the voltages that we have there. Yes, sir.
There, my, the first generator, you have the Y inside, the X is underneath.
Say that again. I didn't understand your question.
The generator on the far left.
Far left, yes.
There's a Y line inside, but then those two on the right, there's nothing inside.
That because this would tend to be shown as a generator. And as a motor, you typically would not show, right? Okay. Those would be loads. Yep. Yep. All right. So we get the diagram, but oh no, we've got a lot of different voltages and S-base values. So we immediately have to convert this to a consistent S-base, right? Make it all a consistent S-base. So, whoops. How do we do that? Well, let's go ahead and try to make this as easy as possible. Let's pick an S-base and a V-base that are kind of consistent. So let me copy this over. Put it on whiteboard. Okay. So it doesn't matter. You can pick whatever value you want, but I'm going to pick S base to be 300. Right? And again, it could be 100. It doesn't matter. It just means you have to do more conversions. And I'll pick VB over 1 to be equal to 20 kV. VB2 is 230. And VB3 is equal to 230 times 13.2 divided by 220, right? Those are our V-base values. So all you need to do now is convert everything to a consistent S-base. So we can see XG is equal to 0.2 or J.2 because that's already on the correct S-base and V-base. We'll call that XT1 is going to be equal to VB old divided by VB new, that quantity squared. Well, these voltages are the same. So I don't have any VB old, VB new ratio that's not 1. So I'm going to skip that. Then we're going to multiply that SB old over SB new. The old MVA is 350. The new is 300 times J.1. XT2. Now the MVAs are the same, right? 300 and 300, so I don't have to do any corrections there. But I do have to correct for the V-base. So that's VB new. No, VB old. Wait a minute. It's VB old over VB new. Yes. So it's 220. So I have these backwards. Sorry about that. That's supposed to be 300 over 350. And this is over 230 times J.1. And for, we'll call that motor 1. I have to adjust both. So I should probably do this quick calculation. Let me bring up MATLAB really quickly. Where is my MATLAB? Here we go. And let's see, 230 divided by 220 times 13.2 is 13.8 kV. So this here is 13.8 K. So I've got to do VB old or VB original divided by VB old times SB new or SB old, sorry. I'm all over the place here. Sorry about that. SB new over SB old. That multiplies J.2. And then the last one, X motor 2, same voltages. Forgot the squared part here. Sorry about that. Times 300 over 200 times J.2. So these both should be equal to the same number. So now I have my per unit diagram, my per unit quantities all on a consistent base. Now I'm going to go back to this diagram and figure out what my positive sequence network is going to look like. My positive sequence network is the only one that contains a power supply. And then I just start including the impedances here, here, if there's one over here, 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 and here. So I don't even have to look if the generator or transformers are grounded or not. I'm just going to blow right through them and draw the diagram. So that's my per unit diagram. And you'll notice I have an impedance of the line associated right there, right? 1 minute. Tell me what the actual line impedance is. Go. Nope. Transformers all have X.
Oh, yeah.
Tick, tick, tick. Nobody's writing. It's not that hard. This should be something you can do very, very, very quickly. What is the actual ohmic value of the transmission line that connects transformer 1 to transformer 2? I guess I now know what you need to put on the final. How many per unit problems have we done?
What was the basis of
I think we picked 300 MVA and 20 kV at VB1. I think VB2 ended up being 230 kV and VB3 was 13.8 kV. Anybody? The minute is up. Who's got an answer for me? Let me back up. Who doesn't know how to start this problem? One person who's honest? Yeah, it's just converting back, right? This is in per unit. How do you go to ohms? You multiply by Z base. So 0.1815. What is Z base equal to? How do I get that? Go ahead. 230 kV squared over S base. Now you can actually calculate what the line actual ohmic value is. Do you have another question or comment or?
No, I've been.
Oh, what is it?
They're not 2032.
Thank you. B? No, I didn't say that. I said there was no line impedance shown. Right? On the diagram. I wanted to see if we could calculate that and get that from that information. So I specifically left that off to see if we could do this part right here.
Oh,
So challenging you all a little bit. But you can look at the per unit, the per unit positive sequence diagram, and it's really pretty simple and basic, isn't it? It's just the generators converted, the generator and the motors converted to power sources, and then we just include the internal equivalent impedances, all corrected to our new basis, right? And you can even tell that's J.2. That's the only one, right, that didn't need to be corrected. it was 20% X for the previous value. See how it's the same one? What's that? You didn't need to. Because the base quantities match the generator manufacturers. Yep. Where the other ones all had to be tweaked a little bit. So that's my positive sequence network. Now, I've got to go ahead and do the negative sequence network, which is going to be exactly the same as the positive sequence network, minus the power supplies. Why don't we have power supplies in the negative sequence diagram? Can you remind me? I was hoping you all could remind me, not the other way around. No? All right, I'm giving you a new job. You're the plant engineer for a new power facility. And you need to go out and purchase a 13.8 kV generator. And you tell the manufacturer, hey, build me a 13.8 kV generator with a voltage source in the positive sequence network and a voltage source in the negative sequence network. What did you do by telling them that? Or maybe they want to sell, let's make it even easier. They want to sell you one that says, look at this. I have got such a quality piece of equipment that I've got voltage sources in both my positive sequence diagram and my negative sequence diagram.
Be two.
No, it's the same generator. I only need one generator, but I can generate negative sequence and positive sequence right out of the factory. You say, yippee-doo, what a bargain. Why not? You're going to lose your job. You don't have an answer.
You don't want, right?
Well, I want current, but I don't want unbalanced systems. If I buy a generator that its voltages are 13.2 at an angle of 0 and 12.5 at an angle of -10 and 12.7 at an angle of positive 125, do I have a balanced system? So plugging that generator in and turning it on with all my loads, now I'm going to get all these neutral currents flowing, and my voltages are going to be different amongst phases. So my motors that connect to it, they're going to spin at weird speeds, or they might vibrate a lot because sometimes I have a lot of magnetic field exposure. Sometimes they have little. So that would be a disaster, a complete disaster. So I hope that you would tell that person, you're not a quality generator manufacturer, if that's what you're telling me, because that actually is not a good machine. So you should only generate positive sequence voltages because you want it to be balanced. If you generated negative sequence voltages, then you got a bad machine, or both positive and negative. So that's why we never, ever, ever, ever should have power sources in our negative sequence diagram, unless your rotation is not ABC, but ACB, which is negative sequence rotation. And then you can have one in the positive sequence diagram. So those are the two diagrams. Look at the zero sequence diagram. That does not look anything like the positive and the negative. So we got to go back here and figure out what to go. Remember, your zero sequence current has to be able to flow into your diagram, right? So if I toggle back over here and I take a look, the way that I draw these is I have a reference bus. And then I start working my way through. All right, I'm coming up from ground. I'm going through that 400 ohm or 400 amp resistor, which is that 32 ohms. Should I put 32 ohms in here? He calculated 32, right? So shouldn't I put 32 ohms in here? Pardon? Remember, it's 3 times the neutral impedance, right? So should I put 96 in here? One yes. Anybody else want to back B up?
Yeah, sure.
I don't trust him.
How could you be what it's
Let's go ahead and put what B suggested in here, but let me make my modification. This is a per unit representation, right? Why would you put 32 ohms in there if everything is in per unit? Close. You think you get a good result if you put in 96 there? One, we saw when we looked at load flow, one, you had a sign change and it wouldn't converge. Can you imagine the wonky results you would get if you got 96 ohms in there? You get some pretty goofy results. All right, so I can flow up through the neutral, so I have a connection. So now I'm going to show my generator. And now it's time to go to the transformer. Can zero sequence current flow into the delta connected winding? No, it can't. So I have to stop right there. No zero sequence current flow. Can't go in or exit the transformer on the delta side. Let's go to the Y side. So the Y side, now we have to start back over because we're at ground. Now the question is, this is a solid ground, so 3 times 0 is 0, right? Can my current leave the transformer? Can zero sequence current leave? Yeah, and it can leave because it circulates over here, which is going to allow it to exit or enter the transformer because that delta connection permits it. Remember, what flows on the primary has to be able to flow on the secondary. So I can circulate my current in my delta. Notice I said in the delta, not exiting the delta, but I can exit or enter the Y. So I'm going to go ahead and put my transformer there. I'm going to put my line impedance there because that is just a transmission line. That doesn't have any impact on the ground, whether it has to go or not. And then the other side of the transformer, can my zero sequence current flow on that side? Well, it's a delta on the other side, which based on the concept that it can circulate around, absolutely. But that has to go to ground, right? Because it can't exit or enter transformer on the delta side, so it has to stop at ground. And then the last one I'm going to do is it looks through motor 1. I can go up, but I cannot go over to the transformer. And let's look at motor number 2, connected over here, but stops right there because I can't get any zero sequence current to flow through the motor because there is no connection to the neutral. So I have to stop there. Yes, sir.
And I'm not sure if we can, the diagram go live on EET421 grounded, like center ground.
Yeah, not center grounded, neutral. Yep. If you were in Europe, they call it star grounded. I guess the Y looks like a star, so that's why they call it star. Yes, sir.
For the center portion
Yep.
of that, are we starting from the delta going to another delta in the center portion?
Starting from the Y, because
Okay.
current can flow through the Y in and out, but it can't flow through the delta. Now, the only other thing I'm going to add is where the buses are. So over here, this is bus 1. This is bus 2. And whoops. Let me show this as bus 3 over here. Because now I've got to go ahead and do my Y bus to get those. So let's toggle back over here because it's in the slide and it's much neater. Those are my diagrams. Questions on how to build those? Positives and negative sequence, piece of cake. Easy peasy. Zero sequence is not easy peasy. You got to really think about it.
Input take time for 1.6.
That's right. But he told me the answer was 32 ohms. That's 21.65. Where do you think I got 21.65 from? 32 divided by V base squared divided by S base, right? I didn't put 32 in there because then I would have also had to put ohms. Do you see any units here? So that's where you get that.
Which resistance you got, the phone line
That's a line, that's the resistance of the line.
from the generator to the first customer.
Nope, that's between the two transformers. This impedance here and here, those are the two transformer impedances.
Yeah. So then what's that?
That's the transmission line. That is the line impedance right here. Connecting the two transformers, because they're not going to be in close proximity to each other. The likelihood that your load is going to be close to your transformer, step-down transformer, or your generator is connected or is close to your step-up transformer is pretty high, but the transmission line might be 50 miles long. So it would have some impedance associated with it.
Now, is it normal the line has a resistance more than impedance?
No, it almost always will have higher impedance. But in this example, I wanted to make it easy for it to scream at you to see what that value is. If I had put another inductor in there, you may be like, hey, you added another inductor. Where's that from? But by showing it as a resistor and the original diagram shows no resistors, you'll be like, ah, that has to be the line resistance.
So both of those resistors are line.
What resistors? I only see one resistor.
What about the
Oh, that's a neutral grounding resistor. That's in the
Okay.
neutral to the generator.
that's
Okay. So now you all can build Y bus for each of those diagrams. Or you should be able to. Well, you've got three buses, so you're gonna have Y bus is gonna be 3 by 3, and you have to draw 3 Y buses or create 3 Y buses. But this is not too complicated of a system, as you can see. Okay. So I put a fault. We're going to assume the fault is at the terminal of the machine. So that's going to be at bus 1. And so I built the Y buses, and you can actually see what the Thevenin equivalent impedances are seen at seen by each of the networks at bus 1. You can see the positive sequence, negative sequence, and 0 sequence. If you don't see that, go back over here and build your Y bus and see if you get that. Okay? Questions on that? All I did was I just did Thevenin equivalent impedances because I'm trying to look at the fault current as a result of current flow for a fault on bus 1. So you can see, hey, let's go ahead and look at the Thevenin equivalent impedances. That's what's going to be what the limiting factor is for a fault on bus 1. All right, so now let's figure out how to couple those networks together. Let's look at the single line to ground fault, okay? And again, we only couple it at one location. We're going to assume that phase A gets the fault, and it doesn't matter. It could be phase B, it could be phase C. We're looking for the magnitude of the current, and since all 3 of the phases are the same, except phase shifted by 120 degrees, if you get the magnitude for one phase, the other 2 are going to be able to do the same. So let's start. Here's a diagram representation of a single line to ground fault on phase A somewhere out on the system. And you can see that I have a fault impedance ZF there with a fault current from phase A going through there to ground. So what I'm going to say is the current feeding the fault for phase A, B, and C, I can set it up as a matrix. So I have a question mark, and then I have 2 zeros because B and C aren't feeding the fault at all. So now I'm going to go to symmetrical component land by multiplying my phase currents by my inverse A matrix. And then what I end up with is all 3 symmetrical currents are the same. They're actually equal to 1/3 times the actual A phase fault current. Now, let's pause for a second. Is there any circuit that you can think of that all 3 of the sequence networks would be the same? How do you make sure that they're all the same? The current coming out of one sequence, going into the next sequence, those are the same currents. And then continuing on, going into the third network diagram or sequence network diagram is the same. How would you go ahead and do that? You get 2 options, right? Series or parallel. Would you put them in series or would you put them in parallel? Put them in series. So I'm gonna put them in series, but I wanna just make sure that my fault, my phase A fault voltage is gonna match the three added together. So if I plug in the value over here, you'll see that I got VA. This is just the definition of symmetrical components. So you're just gonna add up all three. So here's my three network diagrams. Here is my positive sequence. Here is my negative sequence. And here to here is my zero sequence diagram. And then the currents are doing this. They flow that way. So now, if I want to solve for this current, IF positive, it's just a series circuit. I take the voltage, the positive sequence voltage, and I just divide by the sum of the impedances. So I take one at an angle of 0, because we're assuming an unloaded system with a pre-fault voltage equal to 1. And I divide by the sum of the impedances, and I end up with 0.123 minus J 0.873. If I add the three together, then I end up with 0.37 minus J 5.619. If I put in, so if I take my A matrix and I multiply that by 0.123 plus J 1.873, 0.123 plus J 1.873, 0.123 plus J 1.873, and not equals, but multiply, then that is going to be equal to my, sorry, it's really acting quite slow here. It's going to be equal to my phase currents. And if you plug it into your matrix, I encourage you to do that, you're actually going to see that IB and IC are going to be equal to 0. Exactly what we thought they were going to be. There's no connection to the fault. So when I put those in there, we get exactly that value. All right. So one of the things, if you do any protected relaying, and I know some of you have worked in the utility world, one of the things that you'll actually see for a fault current calculation in a relay is somebody will say, what is a 3I0 current? Have any of you who worked in the power utility world, have you seen that?
Yeah.
So basically what they're saying is, what does IA or IF equal? Because it's 3 times the zero sequence current for phase A or B or C. So when you say 3I0, you're saying, what is a single line to ground fault current? But in relaying manuals, they just call it 3I0. They don't even say IA, they just say I0. All right. So to do single line to ground faults, you're going to take all three of those sequence network diagrams, put them in series, and then you calculate IF, then you can calculate IA. If you want to solve for, well, we don't have the voltages, we'll show that in a little bit. But if you wanted to solve for the voltages at the fault, we know that VA is going to equal 0 because that's where the fault is. But what you'd have to do is solve for VA1, VA2, and VA0. So VA1, oh, it's really slow. VA1, the way you solve for it is equal to, let's see, so it's 1 at an angle of 0 minus IA, sorry, it's really slow, 1 times 0.01. When the computer's really slow, everything takes a lot longer to respond here. 0.0175 plus J 0.1288. That's how you solve for it. It's just a KVL loop, right? Same thing over here. I'm looking for the plus to minus, which means I'm looking for these voltage drops here. So VA2 is equal to minus IA2, or not IA2, IA0 or IA2, it doesn't really matter. We'll call it IA0 actually, make it easy. Times 0.0175 plus J 0.1288. And you can do the same thing to solve for VA0. So when you solve for those three voltages, they would sum to zero, but we'll see that as we start chunking through these. All right, so let's look at the line-to-line fault and figure out how to couple those networks. So single line to ground, we put all three in series. Line to line, let's figure that out. So with a line-to-line fault, you'll notice no path to ground, right? There's no connection to ground. It's a fault between two lines. So I have IB and IC going towards each other, but they're in opposite directions, right? So the fault current is going to be equal to zero, the fault current going to ground, but the fault current going from B and C are going to be in opposite directions, right? One's going up and one's going down. IA has no fault current. That's zero. There's no connection. And similarly, we can say that VB and VC are going to be the same because there's a short circuit between the two. So those voltages actually are equal to each other. So let's go ahead and run through our equation. And when we put in the fact that IB and IC are the same but in opposite directions, when we plug that in, hopefully you can see 1 times 0 plus 1 times positive IB plus 1 times negative IB, isn't that going to be in fact equal to 0? Won't those add up to 0? So if I have no zero sequence current, how do I couple in the zero sequence network? That's a trick question. You don't. It's not coupled in. So the zero sequence diagram that you calculated all the way back over here, it stays disconnected. It still exists, but I'm not coupling it to the other two networks. So zero sequence is not coupled, but the other two are going to be coupled. So let's see how we can couple those together. So when we plug in and solve for IF positive and IF negative, we see that they actually are going to be the opposite of each other. If you do the multiplication, you can see that it's alpha minus alpha squared versus alpha squared minus alpha, right? But the magnitudes are the same. So the fault currents are opposite of each other. Can you think of how you would connect the positive and the negative sequence diagrams so that the positive sequence current would be the negative of the negative sequence current? Only two options, right? Series or parallel? If we put them in series, they're the same, right? So we rule that one out. Got to put them in parallel. Because if I have a diagram here, and I'm just going to show it as a box with current going out and connect them that way, doesn't the current that I'm assuming here is IA positive, isn't that going to be in the opposite direction of IA negative? One goes up and one goes up, so they meet in the middle. So one actually has to be going in the opposite direction. So we actually put our positive and negative sequence diagrams in parallel for a line-to-line fault. Okay. Last thing we do is we want to make sure that our voltages are the same, because again, our network diagrams are going to be in parallel with each other, which means that the voltages have to be the same. And so when we plug that in, we end up with VF plus equals VF minus. So yes, we can put them in parallel. So let's apply that to our system. And now we have our positive sequence diagram right here and our negative sequence diagram right here. We just put those in parallel. Even though it looks like they're in series, they actually are in parallel with each other. Everybody have a hard time with seeing that? If you can't see it here, let's just do it this way. I'll call that Z1, 1 at an angle of 0. Here's my positive sequence diagram. My negative sequence diagram is Z2. Now I'm going to couple them by doing this. Didn't I just put them in parallel? Right? The nodes, they share two common nodes, but now hopefully you can see with that wire, if this is IA positive This is IA negative. Don't they have to be the opposite of each other as KCL? And this voltage here, VF positive, is exactly the same as VA negative. So I just put the two in parallel and I get the result. The zero sequence diagram still exists, but it's not connected in any way, shape, or form to the power source. So it never has current flow, but that's okay because there is no ground current. So here's our calculation. We have IF positive is 1 at an angle of 0 divided by the sum of all the impedances. So you just double it up. And now my current is 3.85 at an angle of -82. If I plug that into my inverse symmetrical components, so go back to phase diagrams, basically, our phase currents, I end up with 6.67 at an angle of -172.3 and 6.67 at an angle of 7.74. Is that consistent with what I expect for a line-to-line fault? Well, way at the beginning, didn't we say IB is going to be equal to the negative of IC? And IA is going to be equal to 0, right? Isn't that validated right here? IB is 6.67 at an angle of -172.3. If we phase shift that by 180 degrees, don't we get 7.74? Magnitudes are the same. And my IA is in fact equal to 0. So I do get what I expect. Okay? Questions on the line-to-line fault? Just take the positive and negative sequence diagrams, put them in parallel, and do your calculations. Any questions? All right, and then we can actually solve for the voltages. And hopefully this makes sense too, because phase A has no fault on it. So its voltage should be healthy, and it sure is. It's 1 per unit. Look at VB and VC. They're half of the nominal voltage, but they are the same magnitude, aren't they? Which is what we expect because there's a solid connection between the two. So VA is at 1, VB is at -5, as is VC. They're both at -5. Again, verifying our approach for when we apply the symmetrical components. Let's modify our line-to-line fault and do the double line-to-ground fault. And this is a little bit harder to see, but just kind of bear with me and you'll see. So now we're going to take that same line-to-line fault that we had, and we're going to stick a connection between the two, and then our impedance is going to go to ground. So we don't have the impedance between the two phases. We have it between the two phases connected together and then to ground. So my fault current for phase A is going to be 0 because there's no connection there. My phase B and phase C are going to be the same voltage. That's what's important. That's why we can't have the impedance between the two. And how we can solve for those is they're going to be equal to, again, this is from reference, my fault impedance, whatever that turns out to be, multiplied by the sum of the currents. So now IB and IC don't have to be the negative of each other. They don't even have to be the same. But the fault current is going to be the sum of those two currents. So let's go ahead and plug that in. So we have a 0 sequence current or phase current that's going to be 0. And what we're going to do is when we plug it into our phase components, we see that IF positive plus IF negative plus IF 0 have to sum to 0. Then we can see that by just doing a little bit of manipulation, we have IF 0 is equal to the negative of those two. So let's think about that. IF 0 is going to be equal to the negative of positive and negative sequence. Is there a connection where we can actually achieve that? Is there any way you can couple the networks?
The negative and positive in series in parallel, 0.
So what B said is put the negative and positive. So we'll just go positive, negative, 0. And what he said is to do this. Whoops, put these in series like that. right? And then parallel, I guess we would go from here to here, I guess. Right?
No, that's the perspective.
So that's not gonna work, right? So how would you connect it? You said to put them in parallel, right? Would you agree that those two are, I mean, in series with each other? The positive and the negative aren't in series with each other? Look like they're in series to me. They only share one node. They complete the circuit. So let's put this over here. So maybe what we need to do is draw it, whoops. Draw it a little nicer. Let's go positive, negative, and 0. Like that. Well, the problem with that, though, is we said that IF is going to be equal to the negative of IF plus minus IF minus. Over here, this is IF minus, right? This is IF 0. Do you sum two currents to go to 0? IF positive is right here. Or positive, sorry. I'm not summing them. I'm saying they're the same when they're in series. So that doesn't work, does it? Let's see if we can put them all three in parallel. This is IF or IAF positive, IA negative, and IA 0. This current goes through here, but then comes back and goes through here, and it adds with that, right? So doesn't putting the three in parallel meet that requirement that IF 0 is equal to the sum of the positive or the negative sum of the positive and the negative sequence current? No? Yes?
But then by doing this, the I positive and the I negative, they are opposite. That's what we did previously. By putting that in parallel, they become the opposite.
They are not necessarily opposite, because let's look at the bus diagram here. This right here, this current here is, this is IF negative. This is IA or IA positive, right? This current here can have some current coming from there, but then it can also have current there, right? There are 3 paths on that second node, isn't there? Not just 2. They don't have to be the negative of each other, do they? Just look at KCL. So the only thing we want to do now is check for the voltage and determine, does the VA0 plus, does the VA0 equal VA negative equal VA positive? If those are all exactly the same, then in fact, we can put all those networks in parallel. So we can go ahead and see that VB equals VC. And we already proved that when we did VB equals VC, we did that before, that positive and negative sequence fault voltages are the same. So we've already got those two done just because we have a line-to-line fault analysis that we did. Now we just have to check, does the 0 sequence voltage equal those two? Well, there's a little bit of math to make this work, but you can see where we add some terms in there and we end up with VB equals VF0 minus VF positive. And if we continue on, what we have is VF0 minus VF positive equals 3ZF times IF0. Whoops, what's going on? And let's see. We have this one over here. So what we have over here is we have a VF0 plus VF positive, right? So if we have a fault impedance over here, right? So if ZF is not equal to 0, then we have this term. What if ZF is equal to 0? Then VF 0, doesn't that equal VF positive? If there's no fault impedance, then aren't they going to be the same? They will be. So the only modification we need to make when we put our three networks in parallel, clean this up. So here's our positive sequence diagram. Here's our negative sequence diagram. Here's our zero sequence diagram. These two go in parallel. This over here has to include our fault impedance there. If it's not 0, right? If ZF is equal to 0, then they're all in parallel. If it's not equal to 0, we need to include that voltage drop there. That's what this last step tells us. So all you need to do is put your three diagrams in parallel as long as ZF is equal to 0. If not, you just have to put it in series first with your zero sequence network and then put all three of those in parallel. So here's our diagram. We have our pre-fault voltage. We have our positive sequence in parallel with our negative sequence, which is in parallel with the sum of our zero sequence with our fault impedance. So now we need to do a little bit more circuit analysis because before they were always kind of in series. Over here, you can see that Z2 is going to be in parallel with 3ZF and Z0. So we do a parallel combination first, and then we just have a series circuit. So if you'll notice over here, I have Z0 minus in parallel with Z0. Then I add any 3ZF. For the example that we're doing in class, we're going to state that there's no fault impedance. ZF is equal to 0. So we can simplify this one a little bit. All right, so that's what we have over here. This is the Z negative, and this here is Z0. So I put those two in parallel. I can do product sum. You can do whatever you want. And you end up with 4.58 at an angle of minus 83.3 amps. That's for the positive sequence current. To solve, how would you solve for the negative sequence current? Solve for the voltage, right? If I solve for V1, that means I have V2, and that means I have the voltage going over here, right? So if I have V1, I can get the IA2, and I can also get IA0. So the first thing I'm going to do is solve for the positive sequence voltage drop. So I take my 1 at an angle of 0, I subtract from it the current times Z1, and I get 0.405 at an angle of 1.48. I do the same thing. Now that I know what the positive sequence voltage is, I know what the negative sequence voltage and the zero sequence voltage. So I'm just going to divide each of those by their impedance networks, their Thevenin equivalent impedances, and get those values there. And then at the end, I can see that I get a phase fault current for phase B at almost 7, and for IC just over 7. So remember how I said IB and IC don't need to be the same? You can see that they're not the same there. B.
I need to double what is on VF plus. What is the 1.0 open? And then
I1, this right here is I1. This is Z1. This whole thing. So they're not particularly complicated circuits to do circuit analysis on, right? I mean, this is a pretty simplistic circuit. The problem is if you go to a system that is incredibly complex with maybe 50,000 components and then breaking them down into very simple diagrams. But that's what the programs do when you're calculating fault currents. they build Y bus, they invert and get Z bus, and then they have the Thevenin equivalent impedance seen at every bus. This is for a balanced system. Yes, sir.
And then I minus is minus V of flux, right?
No, so I'm trying to get this current over here, right? So once I know what V1 is, so V1 is a known, that's equal to V2. And to solve for I2, that equals negative V2 over Z2. That's what a negative is right here.
Because they are in the opposite direction.
Yeah, because if you notice, my reference is I have my current going up, but my voltage drop is in the opposite direction. That's where I get the negative. Normally, when you have current going up, it'd be plus to minus, bottom to top. But because my reference is plus to minus here, and then that current, that negative sequence current is going up, that's where I get those values.
And then now in this case, Z1 and Z2 have the same value, right?
Z1 and Z2 have the same value? No, they do not.
So the other one is doesn't Z1.
Let's go back over here. Let's look at our original networks. Those are my three for a fault at bus. Those are the three zero sequence networks to calculate for a fault on bus one.
Yeah, same. Z1 and Z2.
Oh yeah, Z1 and Z2. I thought you said Z2 and Z0. I'm sorry. Yep. Yeah, they're the same. Okay. And out of the three unbalanced fault systems, which tends to have the highest current? Have any ideas? Usually the fault current is the highest for a single line to ground fault. Then it goes for a double line to ground fault. And then it goes for a line to line fault. But I did a project for a Air Force base. I think it was an Air Force base in Connecticut, that they actually had a higher level of double line to ground fault current than single line to ground. That's the only time I've ever seen that. But it was a pretty neat, unique system down in Connecticut. They had really odd, or not odd, but different values of negative sequence impedances that I hadn't typically seen. Okay. Questions? Because here's the summary. Single line to ground, find all your sequence networks, find out the Thevenin equivalent, and put them all in parallel, series. Line to line, all you need is positive and negative, put them in parallel. Double line to ground, find the sequence networks for all three, and put them in parallel. Then just do circuit analysis to find the values that you need.
So in the real world, would you just like, if you didn't know what the fault was, do all three, or would you try to find out what the fault is?
So it depends on what you're trying to do. So if you're trying to do like setting the faults, trying to determine what the fault current settings would be for a relay, what you would typically do is you would run, you would most likely run the three-phase fault. That tends to be the highest. And then normally ground fault current is so low, you don't have to run it, but you can, as a backup anyway, you could do all three of them, because it's usually just an option you can click. It's pretty easy, right, to go ahead and do these. But when you're setting them, like actually setting the relays for a single line to ground fault to protect, or double line or whatever, then you have to go ahead and start doing a lot more nuances. And by far, and out of all the work I've done, the hardest protection to set is ground fault settings, by far. Because you have mutual coupling between zero sequence networks. I was telling you about a story how, Eversource had some settings that ended up tripping off Millstone, the entire Millstone generating facility, when it was running full out on a Sunday morning. They had that unusual event. The reason why that tripped is because they had some bad settings in a relay. But you can also get like things chasing you. It's very, very complicated. There's a lot of steps that need to be done to make sure your zero sequence settings are correct. But yeah, you could check them all. But I usually only normally check three-phase fault and single line of ground, because it's so atypical to see those other two have a greater impact. And usually you're trying to coordinate the worst one, because anything beyond that is going to be slower because it has lower current values. So you worry less and less about the line to line and double line to ground. Because it's just gonna take you longer to trip, but that's okay, because you have less energy to cause problems. I'm not saying don't trip, but you don't have to take as long. So you might want to check those to make sure, if you have a line-to-line fault, is there enough fault current to actually get your system to operate, to detect it and trip? That would be a kind of a cautionary tale. Okay, questions on setting up networks? Because that's when their homework assignment, right? Did you already see what the homework assignment is? Taking that system for the Dolby Power facility and figuring out which is the worst fault current, which bus and what is the fault. So that's where it's going to be very, very helpful to build your Thevenin equivalents and have your pre-fault voltages for an unloaded system and go through all that process. All right, before I lose anybody, any questions in TV land or in-person land? Feel okay?
Yep,
All right.
sounds good.
One-
Thanks.
What's that?
Sounds good. Thank you.
Okay. All right. There's nothing else. Have a great day, everyone. And I will see you all on Thursday. Take care.